In this lecture, we'll learn about nanotribology. So, with the advent of nanomaterials, we learnt about how nanomechanics is really essential in terms of dictating the mechanical properties at nanolength scales. Similarly, for when we have some mating surfaces and when we have some intermediate contact between two surfaces, we need to learn about how the response of one surface with respect to other will be, so that we can design engineering materials with much more effectiveness. Like if you want to induce some lubrication, or we want to see the response of one material with respect to other, or see what will happen between two articulating surfaces, we need to learn about nanotribology, and nanomechanics actually goes hand in hand with nanotribology. So, if we define nanotribology, it is a dynamic interaction through relative motion of two contacting solids, and it automatically will involve how the response of one material with respect to other material will be when the materials are in contact and they have some relative motion between those two contacting surfaces. And in nanotribology, the interfacial phenomena of small scale, basically of nanostructures, is very critical. We can also talk about molecular lubrication, like if we can assemble some monolayers on top of a particular material, and then we can see response of the contacting surfaces. Then in that case, we can learn about how we can reduce the friction and enhance the life of a particular for a particular component. Also, in terms of articulating surfaces, the bulk response, the micro response and the nano response, they can be very different mechanisms might be operating at those three different length scales. So, it becomes very essential also to see what is the initiating mechanism, because that will dictate how the crack will basically initiate, and then later on the crack propagation and more at micro length scale, and then the ultimate failure at macro length scale. So, be able to relate them at three different scales is very essential. So, that is why we need to learn essentially how the contact is inducing damage at nano length scale. So, that is why nanotribology becomes very important. So, again nanotribology is not only related when the two materials are closer, but also that how the interaction will occur when when the surfaces are separated. So, nature of interactions when surfaces are brought closer as well as when they are separated. So, that is how we define nanotribology. So, first of all, it is a dynamic interaction through relative motion of two contacting solids. So, we need to see that the two articulating surfaces are in contact, and then it is defined by interfacial phenomena, specifically at small length scales of nanostructures, because nanostructure will again define the contact between the two mating surfaces. So, that also is very essential, that what is the structure at nano length scale, and that can be helpful in dictating the molecular lubrication or engineering the articulating surfaces or articulating contacts, or even in microelectronic mechanical systems, so that we can see how is the contact leading to such damage. And also the nature of interaction when the surfaces are brought closer or when they are separated, it also both of these entities are now constituted in the nanotribology. Essentially, the contact in materials, when we have a when we see things at a much more at a bulk scale, we realize that the contact is complete. So, we can see we have one surface and then we have second surface. The contact between them is very nice for a flat surface. But again, if we can start zooming it to very high magnification, we will realize that the surfaces are not smooth, they are not optically smooth, but they have some perturbations. These perturbations can be at micron length scale, or they can again be at a nano length scale. So, we can see that we might have some contacts which are very different from those are defined by bulk scale. So, in this case, bulk length scale, we might see that we have a complete contact, whereas in the case of micro or nano, we will realize that the overall contact surface has gone drastically down. So, essentially where we had a complete contact like in the bulk scale, at nano scale we will realize that we have only a limited contact. So, once we are talking about nanotribology, what do? We take the surface, we capture the surface roughness as it is, and we utilize a probe which is small enough to contact each and every asperity. So, in this case we can utilize an indenter with certain cantilever. So, we can see this is our surface. Again we are talking about micro or nano asperity, and we have a tip which is small enough, tip or probe which is small enough to capture each and every entity or each and every point of this particular surface. So, in this case what we are talking about? We are talking about contact of single asperity. So, all these nominal points which were kind of abrupt and then they were not in contact in the bulk scale, because if you see at the bulk scale these are certain areas which are not in contact at all. So, like this surface they are not in contact at all, but again they also will dictate the overall friction that will occur in a material. So, what is happening at nanoscale? We can now capture the contact of single asperity. So, we can scan this tip along the surface and it will try scanning the entire surface without losing any contact. So, what we can get here is we can get a localized information in this particular case. So, also in this case if we find that if we have more than one type of a material, what we can do is we can now say in this case we had phase 1 on this region and phase 2 on this region. So, as the tip is moving along, it can capture easily the values, the kind of friction which will occur in phase 1 and in phase 2. So, now we can differentiate what is happening with respect to the isolated contribution from each region or each phase. Even the orientations can also differ from surface to surface. So, what can happen is that their contribution might also be very different. So, what we are seeing in respect to contact in materials, what is happening is now we can capture the local asperity contact. We can also differentiate what will happen once a tip is now in contact with the each and every individual phase. So, we can find out the contribution from each and every individual phase rather than the complete interaction. So, in micro or bulk wear we are getting an approximate or the average property of the material, whereas in case of nanotribology what we can do, we can find the overall response from each and every individual area. Now, we can combine it and then we can correlate it to the micro or the bulk scale. There might be very different phenomena, because at micro scale there might be certain contributions which might enhance because of the presence of grains, because grains can also orient, they can also induce some damage via their rotation or their swirling or any such or even their growth. So, that can be captured at micron scale, not at nanoscale. So, nanoscale will only find out what is happening within a particular grain. Micron scale will tell contribution of the individual or localized response plus the grain response, and at bulk it can be multiple number of grains which can lead to damage. It can be even 3 body wear which can occur in a bulk material. So, we can see the contact in material is very essential component, because at bulk length scale we are talking about only a flat contact and we assume that it is in complete contact, but in reality at micron or nano length scale we can see that asperities are not in contact. So, to extract the information, localized information, what we are doing, we are allowing a tip or a probe to scan through the surface and provide us the localized information, isolating it from the bulk. So, learning about the friction at atomistic scale, what is happening here is we can utilize two techniques. We can either have the topography or the frictional contribution. So, topography is nothing but scanning the surface and finding out what is the local arrangement of atoms. So, if we take a highly oriented pyrolytic graphite, so what will happen, we will see the regularized hexagonal structure. It will be highly regular pyrolytic carbon structure. So, we will see that we have this atomistic position. I am not drawing it that regularly, but we will see that we have very regular arrangement or hexagonal type of arrangement of atoms through the topographical scanning. But once we talk about frictional forces, if we can scan the same thing, because there will be some frictional contribution from these atoms, and say if we have a tip which is very fine and it can capture the contribution from the atoms, what we will see? We will see the same periodicity. So, if we capture the image again by utilizing frictional forces, what we can see, that we have the similar arrangement, same periodicity can arise from the scanning. So, we can see the same periodicity from the scanning now, the same hexagonal type of a structure will appear, but we will realize that the location of this atom and this atom, the corresponding atom, through topography and through frictional forces, they do not match. There might be some shift between those two atoms. So, what we can essentially see is the displacement of peak with respect to each other can occur in the highly oriented pyrolytic graphite, because the maxima of the interatomic forces in normal condition, because in this case we are utilizing normal forces, and in the second case we are utilizing the lateral forces, because we are considering friction. So, the maxima of this normal forces and lateral forces, they do not conquer at the same point. So, that is why we can see some shift in the peak location. So, essentially what we will see, say in the first case what we had position of all these atoms. So, we can draw that. Let me just draw one or two layers so that it becomes a little clearer. But once we start utilizing the frictional forces, what will happen? We will see that there is some shift. So, these positions would have shifted to certain extent, but it will now maintain the periodicity. Periodicity will not be affected, the periodicity remains the same, it is only the location which has been shifted now, and that occurs because of some atomistic scale stick slip processes. So, the tip is in contact with the atom, it will have some sticking and slipping process which can occur when it is in contact. So, that is why we will see the difference between the normal and the lateral forces imaging. So, that is the case with the frictional or the normal force imaging at the atomistic scale. So, we can see the topography and friction, they exhibit the same periodicity, and the displacement of peak can occur once we are talking about the normal forces or the lateral forces, that results in the shifting of the peak location, and that occurs because the interatomic forces and the frictional forces, the maxima of these two forces does not occur at the same point. So, these positions differ in the normal and the frictional forces, and that occurs because of the localized or atomistic scale stick slip processes. So, that basically tells that once we are imaging it and once we are doing a frictional force analysis, it means that we can attain the same periodicity, but without exactly locating the exact position of these atoms. So, seeing the friction at micro scale, we can see that once we can cleave the highly oriented pyrolytic graphite, we can see, or because of different orientation which are present on the surface, or because of amorphous region in the HOPG, that is a highly oriented pyrolytic graphite, what can happen is the coefficient of friction can alter to a certain extent. So, once we are talking about the cleavage or presence of some amorphous phases on the graphite, we can see the coefficient of friction has now drastically reduced by more than an order of magnitude. So, that basically tells that the orientation of this crystals also is very important in terms of identifying the slope or the coefficient of friction. Again, it has been identified by researchers that it is not the peak, if you have, say if you have a rough surface, it is not the peak position or the height of a asperity, it is the slope of that asperity that decides the dependence of friction on that particular feature. So, once we are talking about roughness, it is not the height, but it is the slope of the asperity which decides the coefficient of friction. And how does it occur, we will see in a later few slides, but let me just give you an example. Say if I take a surface and I basically dig out a hole in it, and that hole should be much smaller, should not be very large. So, say if I have a small asperity a depth of say around 50 nanometers, not more, but let us say around 50 nanometer. So, what we can do, we can allow a tip to scan through this line. So, it will experience a very nominal coefficient of friction along this side, but as soon as it is touching this surface, we will see a dip. So, if we just talk about thickness of this one, we will have very smoothness, goes down by 50 nanometer, and then we again come to the surface. So, we can see that it is around 0 and this is around say 50 nanometer. But when we talk about friction going from left to right, what we will see is that we have frictional force on this side and distance on this side. So, as soon as it is going to certain value, so we might have some value of coefficient of friction, very marginal value of say 0.01, 0.02, very minimal 0.1 or so, very lower value of coefficient of friction. What we will realize is that frictional force will coefficient of friction or this frictional force will drastically reduce as soon as it will touch this particular point. So, let me mark it red so that you can see it more clearly. So, as soon as it is reaching this point, we will see a dip in the frictional force, and if it goes along, we will see some again back to normal, and it will go on, and as soon as it will touch again the ascending asperity, what we will see? We will see a dramatic increase in the frictional force. So, what we are seeing? Very high friction at point number 2 and very low friction at point number 1, and then coming back to normal. So, that is what we can see. So, with the distance what we are seeing, as soon as the tip is descending, we can see a lower decrease in the frictional force. As soon as it is seeing the ascending asperity, we can see very high level of friction or very high frictional force that can occur at that particular point. So, that is point number 2, we can see very high friction. At point number 1, we can see very low amount of friction. So, that is telling basically that there is some dependence of friction on the local surface slope rather than the surface height, and that part has been already proved by certain researchers. But why does this happen? We will see in a slide or two. So, talking about the friction mechanisms which are dominant, we can see that this difference in the coefficient of friction, it can be explained via the certain mechanisms. So, adhesive forces, if only adhesive forces are present, they will not be able to explain the local variation in the friction, because material is the same, all the conditions are same, and coefficient of friction is given by force by the normal force, frictional force by normal force. So, essentially it is not responsible for causing the change in the coefficient of friction. So, addition cannot really explain why this variation is occurring in the coefficient of friction. Then we talk about addition and roughness. So, we talk about this ratchet mechanism, and that is basically led by asperity contact and its angle with respect to the horizontal plane. Once we have an asperity, then it will eventually make some contact angle. The contact angle will not be normal anymore, it will have some angularity associated with that. So, that basically now depends on the leading or the trailing slope, and that in turn will affect the coefficient of friction. Again, coefficient of friction can also be dependent on the plowing, but when we are talking about nanotribology, the frictional forces are in the case of this imaging, frictional force imaging or microscopy, what is happening is that plowing is very much limited, because there is a very limited damage in the frictional force microscope. So, tip sliding can occur in either direction, and the plowing can be it will be very limited, and the damage will be very limited, because our forces are not exceeding the plastic deformation, it is not leading to plastic deformation of the material. So, in that case it is the plowing is very much limited. So, we can see the alteration or the change in the coefficient of friction is occurring because of the slope of the material, and that is being dictated by the ratchet mechanism, and that is arising from the roughness of the sample. So, we can see that friction mechanism which are dominant are adhesive or adhesion, ratchet and plowing, and adhesion is totally material dependent. Plowing also will depend on the kind of deformation or the kind of damage that is occurring, and in this case frictional force microscopy, we can see the frictional forces are very limited, very low. So, in that sense it will not lead to the plowing of the material. So, the eventual contribution is coming from the roughness, and that is now dictated by the ratchet mechanism for the friction, and that leads to some asperity contact angle, and because of asperity contact angle, we can see the horizontal angle basically changes. The surface is no more horizontal. So, it has some angularity with respect to the applied force, and that in turn leads to change in the coefficient of friction. So, that is what it is, and how does it exactly depend? We can see in the next slide. So, essentially we can see the coefficient of friction is given by frictional force by the normal force, but once we have a slanting surface, what we can see, let us say we have a slanting surface, then what will happen, we will have some theta with respect to that, and this is the area where we are scanning it, and then we have a probe tip. So, we are seeing this. So, tip is moving in the right hand side from left to right. So, what we can see, we have this frictional force which is arising out here. Then we also have a normal force contribution. So, we have a normal force which is also existing out here. So, in that case, what is happening is, if the tip is moving from left to right, what we can see that in the case of ascending, so when we are going from left to right, this tip, this probe or tip is now experiencing some additional contribution because of the resistance of the surface. So, what we can see, the coefficient of friction is now given by mu naught plus tan theta divided by 1 plus mu naught tan theta. So, mu naught is nothing but the normal part without any when the surface does not have any slope. So, that part is now equal to mu naught plus tan theta. So, there is some additional term. So, as soon as the there is some contact of this probe tip with respect to asperity, we see some increase in the coefficient of friction. So, that is why as soon as we see a ascending surface, we see that coefficient of friction basically now increases. In case of descending, what we can see is, so in this case, if we had the same contribution, but now tip is moving from left to right on the right hand side. Now, we can see the similar forces which are acting on it, but now in this case what we can see, there is some release, because once we have contact surface, there is some contact resistance because of the asperity. In this case, there is the drawing away from the surface. So, in this case we can see the contribution is mu naught minus tan theta for lower mu naught and theta values. So, we can see that mu is equal to mu naught minus tan theta. It means there is some decrease in the coefficient of friction. So, we can see for lower mu naught and theta values, we can see that this term can be ignored. So, the denominator will become only 1 in both the cases. So, this term can be ignored for lower mu naught and theta values. So, eventually what we see, the overall contribution is coming because of the ascending and descending surfaces, and because of this theta value, because of this angularity, because of this particular slope. So, we had this sample, and the sample surface we had certain theta value associated with that. So, we can see there is some theta value, angularity, and then we have a force which is now being provided to the probe tip against the surface. So, when it is working against the surface in an ascending fashion, so we can see for an ascending surface, we can see there is some additional resistance which is occurring because of that, and that is given by mu naught plus tan theta. Whereas, when the tip is getting retracted or it is moving away from the surface, now it also finds a release. So, that is being given by the descending surface, and we see a decrease in the coefficient of friction. So, that is how the coefficient of friction depends on the surface slope. And again, if we can see the frictional forces the same way. So, they are higher at the leading edge. So, once we have a leading edge or the ascending surface, we find that we have a positive slope, and that induces some additional torsion of cantilever beam also. So, once we have a slanting material, so slope is positive. So, as soon as tip will encounter that, it will experience some additional torsion at of the cantilever beam, and that in turn will induce very high frictional stresses, or the shearing of the material will require much higher stresses. So, that is the reason it also experiences an increase in the coefficient of friction. Whereas, in the case of trailing edge, so when we are retracting or when we have negative slope, there is no collision effect. So, there is no additional torsion or shearing that is occurring in the tip, and that leads to lowering of the coefficient of friction. And the ratchet mechanism is considered out here, because also we assume that the tip is small enough when compared to the asperity, which is around 100 to 200 nanometer. Assuming that, so the tip also has to be small enough to capture the ratchet mechanism. So, if the tip is pretty high, it cannot it will encounter more number of asperities altogether. So, in that case, the contribution of ratchet mechanism may not be that large, but again it will be substantial. So, again we can see that for higher frictional forces at the leading edge are caused by the torsion of the tip itself. Also, very high shearing forces are required for the friction, and in that term we can see the increase in the coefficient of friction. Whereas in case of trailing edge, we have a negative slope. So, there are no collision effects of the tip with the sample surface. So, in that sense we can observe a very low coefficient of friction, and we assume that the ratchet mechanism is dominant, because the tip is assuming the tip is pretty small, around 10 to 15 nanometer, the tip radius will be around 10 to 15 nanometer, whereas the asperities are generally 100 to 200 nanometers. So, assuming that, we can assume that the ratchet mechanism is the dominant factor in controlling the coefficient of friction. Again, now there can be various considerations for calculating the frictional forces. So, there can be two main effects which can come by, there can be many more. So, one main mechanism is material induced effects or topography induced effects. So, once we are talking about material, we are talking about the phase, its composition, its homogeneity, such aspects. So, once we have a material contribution, they are independent of the scanning direction. So, it does not matter if we are taking the tip from left to right or right to left, and we are not worried about the topographical features anymore. So, we just worry about the material composition. So, it does not matter whether we are going from left to right or right to left, the features will come out, the overall properties will come out to be very similar, because those are dependent on the material and not on its feature or the topography of it. So, what essentially we are worried about is the phase, what is the constitution of those particular phase, what is its composition, what is the homogeneity, and also what is the final response of the material with respect to a force which is applied by a certain tip. So, we can see the first is material induced effects, second can be topography induced effects. It means we find some slope, we find some cavity, we find some hill in a feature, that can also induce some changes, and those effects will change as we are talking about forward or backward scanning. So, as we saw earlier, if I have a feature like this and I am scanning from left to right, then I will observe it, I will observe the initial point as a ascending asperity, and later on I will find it a trailing edge, and the first one will be the leading edge. But once I am scanning from left to right, I see that the overall frictional forces will totally change, because now I will find this one as the leading edge and this point as a trailing edge. So, now initially when I had the leading edge, I saw an increase in the coefficient of friction, and in the second case it was reduction in the coefficient of friction, whereas in the second case what is happening is the coefficient of friction is now increase in the leading edge on this side, in the trailing edge I can see reduction in the coefficient of friction, and these are totally opposite. So, that is what we can see, that once we have some topography induced effects, the sign of frictional forces changes completely. So, that is the importance of this topographical induced effect. So, it very much depends on the direction of the scanning. And again one more consideration which is to be given necessarily for engineered surfaces, all these features, all the topographic features are not symmetrical, they may not be symmetrical, and also it depends on the geometry of the tip also. If I say I have a conospherical tip, it is fine, spherical tip, it is fine, but once I have a non-symmetric tip, say if I have a Berkovich tip and I am scanning it like this, it is, the features will be very different, because now I have some different area which is now coming in contact. Or if I do scanning like this, so in this case I have a pointed area which is now scanning the surface, in this case I have a slanted surface, and in third case I have a flat surface which is now leading to scan the material. So, all the responses in all the three cases might be very different depending on the material response, but definitely they will be different, because in one case I have a pointed tip, second case I have a slanting tip, and third case I have a flat tip which is now scanning against the surface. So, I will see three different responses. So, that is also very critical, that what is the leading edge of the probe or the scanning tip. So, we can see for consideration for the frictional forces, these can be material induced effects, but they will not affect the overall properties, they are independent of the scanning direction, they depend only on the phase, its constitution or its response. Whereas topographic induced effects, they are very much dependent on the scanning direction, whether forward or backward scanning is being done. So, somehow we can now combine these two together and subtract the effects which are coming from each other. Say in one case I saw response like this, it means I have a trailing edge in this case, and in the second case I had a leading edge. Then I do a reverse scan, it means my leading edge becomes a trailing edge and the trailing edge becomes my leading edge. So, in this case I will see response which is like this. But if when I combine them together, what I am seeing is I will see an overall response which is like this, because the resistive forces are very dramatic. So, it should be the other way actually. So, the trailing edge, it is the negative side on the top hand side. So, let me redraw it. So, what happens in this case, in the trailing edge I will see a reduction in the coefficient of friction, and in the leading edge I will see a enhancement in the coefficient of friction. Once I do a reverse, I will see the exact opposite trend. So, in this case my now forces will be very high. So, once I combine them together, what I will see is something like this, because in this case the leading edge the overall coefficient of friction or the frictional forces are dramatically high in comparison to the trailing edge. So, I will see a response which is more like this. So, it is very hard to correlate them, that oh, this effect and this effect they are similar of trailing and the leading edge. So, combining them is little more trickier rather than so simple. So, we can't really combine these two forces as it is. So, it requires some engineering as well or some understanding of this as well. So, those are topographical effects, and also asperities effect can also come into picture because of the tip geometry or the leading or the trailing edge of the tip itself. Also, the environment also has a very dramatic effect because response of any tribocouple will depend both on the surface properties of the two mating surfaces as well as the tribological interface with the environment. So, depending on that, so first thing is the surface properties, biological interaction, tribological interaction, and what is happening exactly at the mechanics, what is the dominant mechanics which is leading to the contact and the response of these two. So, those couple of properties which are very important are the surface properties, how this tribological interaction is occurring at the interface, and also what is the mechanics, dominant mechanics that is leading to this particular response at the tribological interface. Again, friction and wear can lead to damage of either one or both the materials of both the mating surfaces. So, frictional force will be dominant at both the surfaces, and that will lead to some damage accumulation in the two mating surfaces. So, now let us see the role of humidity. So, we can see that the role of humidity, how it can really occur. So, the interaction between tip and sample surface, there are very many van der Waals forces or the secondary forces of attraction, and also there is some meniscus formation. Once we have humidity, always there will be formation of some meniscus. So, what will happen, that adhesive forces will start increasing as we start increasing the relative humidity because of formation of meniscus bridges. So, once we have a tip and a sample, and there will be some secondary forces between the tip and the sample, van der Waals forces of attraction, or it can be even meniscus formation. So, once we are contacting the surface, so once we are contacting it or when we are separating it, we can experience those forces come into play. It also will depend on the distance between the tip and the sample as well. So, that is what is very critical, that depends on the distance also between the sample and the tip. So, as soon as we see, as soon as it is coming closer, we might have some attractive forces, but once they are very close, there will be very sudden increase in the attraction forces. Similarly, when they are trying to separate, initially we will find a very high resistance, and there will be sudden jerk, this sudden jerk. So, with a very high jerk, these two surfaces will now separate at certain distance. So, we can see once they are farther apart, very smooth transition from higher to lower distances, and there is sudden grasp or sudden capture of these two surfaces with a sudden force even for attraction, and when they are separating out, we will see the same phenomena. We will see the same phenomena that they will now separate with a very sudden force. So, they will separate far apart. It is more like a magnet. Once we try to bring the two magnets closer, they will find at certain point they will combine together with a very high force, and similarly once you are trying to pull them apart, it will be very hard initially to separate them apart, but as soon as you reach a certain distance, they will go much farther apart with a sudden force. So, that is what we can see, that the role of humidity, it induces some attractive forces which are van der Waals forces, and also because of meniscus formation, and as soon as we increase the humidity, we will see that adhesive forces also start increasing, and it happens because of the formation of meniscus bridges. It also depends on the distance between the tip and the surface, and again the role of humidity also basically gets affected by the roughness or even the hydrophobicity of the material, because once we have a hydrophobicity or the wetting of the material, in hydrophobicity we won't allow a continuous film formation. So, in that what can happen, we can form only local islands of water film, and that in turn is not covering the entire surface. So, we can see the enhancement in the shear forces or the frictional forces which can occur out there. There can be again role of tip radii. So, apart from the effects of the environment like humidity, we can also find role of tip radii. So, what is happening here is, when we have a higher tip radii, we find that the contact area also increases. So, once we have higher contact areas, now we require higher shear forces, because now we have higher contact area. So, once we have higher shear forces, in addition we also find that the van der Waals forces also will increase because of the enhanced contact area. So, eventually what is happening is the overall shear forces or coefficient of friction also starts increasing. In addition, once we have a presence of humidity, we also see increased meniscus effects. So, what is happening is, if we for a particular tip, if we see the relation between coefficient of friction and relative humidity, in the initial region we can see an increase in the coefficient of friction, because in the initial region the number of aspirated contacts will increase because of formation of meniscus bridges. So, in the starting region we have more meniscus bridges, very high adhesion forces, very high van der Waals forces. So, now we require very high shear force, but at later on some time what happens is, now this film starts making complete coverage, and because of that it starts acting as a lubricant, and now the contact will require, now the tip is submerged and now it will require very lower shear forces for moving along, and in turn it renders a very low coefficient of friction. So, we can see the role of tip radii. So, as soon as we have very high tip radii, it means we have enhanced contact area, which eventually means we have very high van der Waals forces. Also, now we require, because for larger contact area we require very high shear forces, we have high van der Waals forces. So, eventually we will see an increase in the coefficient of friction. Humidity also, we can see there is a downward bell type of a curve. So, initially we see that with enhancement in the relative humidity, we see an increase in the coefficient of friction, because now we have very high meniscus bridges, very high contact area. So, that in turn will start increasing the coefficient of friction, but at certain stage it will start forming a continuous film and it starts acting as a lubricant. So, in turn it now starts reducing the coefficient of friction. Also, this dependence of coefficient of friction on the length scales. So, coefficient of friction depends on the length scale as well. What is happening, what has been observed is that nanoscale friction is much lower than that of a micron scale friction, and that basically results because the contact stresses are very low. So, it means the contact stresses are much lower than the sample hardness. So, what happens is, because of that is that the overall plastic deformation is much more limited at nano scale friction. So, we can see nanoscale friction, it is the overall coefficient of friction is much lower than that of a micron scale, and that essentially arises from the contact stresses, which are very low, much lower than the sample hardness. So, we can minimize the plastic deformation that occurs at nanoscale friction. Also, higher indentation hardness, which is observed at nanoscale because of low contact area and low loads, which are utilized in the for the nanoscale tribology. Also, the surface properties, also because of surface properties itself, we observe a very high indentation hardness at the surface than in the bulk. So, that also results higher indentation hardness at nanoscales. Third thing is, because of lower loads and lower contact area, we can minimize the third body plowing. So, because the overall stresses are so low at this scale that it minimizes third body wear. It means we do not allow any debris to form at this nanoscale friction. So, the plowing is also very minimal, the loading also is very minimal, there is no third body wear. So, in that case, and again even if we find some particle to get embedded, the smaller area of the tip disallows any major damage because of third body wear. So, that also reduces the overall dependence of this coefficient of friction on the third body interaction. And also we have seen that the coefficient of friction also decreases with lower tip radius because of lower contact area. So, eventually what we can see is that nanoscale friction or the coefficient of friction is very low in comparison to that of microscale friction, and that occurs because the contact stresses are very low, because the kind of loading we are applying is very low. It means it is much lower than the sample hardness. So, we are minimizing any plastic deformation in the material. Secondly, the surface itself will have very higher hardness, higher indentation hardness at nanoscale. So, because of lower contact area and low load, that also eventually reduces the frictional forces at the nanoscale friction. Also, there is a minimized third body plowing because of lower loads and smaller area, and also we have seen that when we have the tip radius is also very fine, we also see a reduction in the coefficient of friction. And the coefficient of friction basically is dictated by Amonton's rule, that coefficient of friction is independent of any apparent contact area or normal load. So, that thing has been very well established for the micron or the bulk scale, that the coefficient of friction will not depend on the apparent contact area or the normal load. So, whatever will the normal load, it automatically will set the apparent contact area, and that in turn will make the mu constant. So, it is not dependent on the normal load or even the apparent contact area, but that is basically being adjusted automatically. So, but this is no more true at the micron or nano scale, because what is happening at the bulk scale, we are also inducing some plasticity. The force or the stresses are high enough to cause the material deformation at that length scale. So, it automatically takes care of the normalization of this normal force and apparent contact area, but that is no more true in the micron or nano scale, because in this case we are limited by the lower force, lower contact area, and there is no more plastic deformation. Also, we are limited to surfaces, so surfaces also will have very high indentation hardness, limited plowing, limited contact area. So, what is happening here is, so at higher loads only the plowing becomes dominant, that is for the micron scale or the bulk scale, and also the, so basically the overall coefficient of friction will be very lower in the case of nano scale. And if you want to match what is happening at nano scale and at micron scale, we need to now see that we utilize very high loads. So, only at higher loads this plowing mechanism becomes dominant, and then only the coefficient of friction values at micro and micron scale or even a nano scale, they will match. So, we can see that the Amounton's rule, which states that the apparent contact area and the normal load do not affect the coefficient of friction, that is no more true in the micron or nano scale measurements. So, for achieving that, we need to make plowing also become dominant mechanism, that can occur only at higher loads, and that only will make coefficient of friction to be similar in both micro as well as nano length scales. So, again we can do scratching both at ramping load or at even at constant load, but if we are utilizing a ramping load, then we can essentially see the response of loading condition as we go along. So, we start increasing the load. So, we have a distance and then we have a loading. So, we start increasing the loading as we are going along a distance. So, we can see that with increased loading, at what point we can see an increase in the sudden increase in the coefficient of friction. So, we are seeing a normal loading which is being applied. So, we can see a normal loading which has been applied to a material as the distance is going along, but at certain point what we can see is that at certain point the coefficient of friction suddenly starts increasing. It is now increased to certain extent and it will keep increasing further. So, at this particular point we can see that the material damage has initiated. And this particular point is the one where we can see this is the critical scratch resistance. So, we can find this is a critical load at which the material starts scratching dramatically. So, with a ramping load, we can see load at which the coefficient of increases rapidly, that is called critical load. So, this is nothing but the critical load which is being applied on the material, and this is a measure of scratch resistance, because after this point there will be very heavy damage to the material. So, we can see the scratch will start inducing to a very larger depth, and that is the responsible culprit for enhanced coefficient of friction, and we can see the load at which the coefficient of friction will increase very rapidly, that is called critical load, and this critical load is a measure of scratch resistance of the material. So, we can realize that if you are using a very soft material, this normal load will suddenly start increasing. At very low normal load itself we can see the coefficient of friction start increasing, but for a very highly resistant material we can see that the normal force can be very high and still the coefficient of friction can be very low. So, we can see the normal load can be very high for wear resistant material, or in other words we require very high normal load for causing the scratch in the material. So, once we have a polymeric sample, we can see that the normal load is occurring at very lower normal loads, whereas for ceramics or very high hardness materials we can see that the normal load is pretty high when the coefficient of friction starts increasing rapidly. So, that is the difference between the soft and the hard materials, and we can utilize this concept of coefficient of friction with respect to normal load to identify the behavior of materials also. Again, the wear mechanism can take various forms. So, initially it can start making some wear marks, or it can also induce indent marks. So, once we allow a tip to interact with the surface, because of the contact between the tip and the surface, if the tip is very hard, it will induce some wear marks on the sample surface, and eventually what can happen is it can also induce some debris, wear debris. So, once it is plowing the material, we can see there is some material removal that also occurs in a occurs because of the tip to material or sample interaction. So, first thing is we can induce some marks, damage marks. If the marks, if the tip is hard enough, load is high enough, it can start plowing the material, that will lead to material removal. Also generally it has also been observed that there can be formation of thin film as well. So, once a load is being applied, and because of localized heating or disturbances or local oxidation also can occur, and that may lead to thin film formation, or there might be reorganization of the material, soft material, and it can also lead to formation of a thin film. Also local deformation can also occur depending on the tip geometry. So, those can lead to formation of deformation bands, or it might also lead to straining of the material. Eventually, if the material is brittle enough, it can also lead to crack generation and propagation. So, if material is enough strain hardened or the material is highly brittle and the loading is pretty high, it can lead to crack generation as well as its propagation, and that might eventually lead to some material removal as a debris also. So, we can see that we have various wear mechanisms. It can have wear marks, might arise because of indent marks. We can have wear debris that might lead to material removal. We can also have thin film formation because of local disturbances or heating or oxidation or even disturbances. We can see local deformation, so leading to deformation bands or straining of the material, or even plastic deformation of the material, which can eventually also lead to crack generation and even propagation of even brittle materials. And one more important concept in tribology is also lubrication. So, we can have various types of lubrication. We can have some lubricant layer, and those lubricants can be either chemically bonded. So, we can have, or they can be also self assembled monolayers. So, we can see that chemically bonded lubricants, it is mainly by the adsorption of water on the surface. It leads to formation of meniscus. So, we did see that with enhanced relative humidity, initially it starts inducing very high frictional forces, but at certain time it becomes a lubrication, and then it starts reducing the coefficient of friction. And this choice of this chemically bonded lubricant also depends the way it changes the viscosity, how it affects the surface properties. So, those are also important contributions in choosing a particular lubricant, which can be chemically bonded to a particular surface. And also talking about hydrophobicity, once you have hydrophobicity, the lubricant will not stick evenly to the surface, it will start forming certain islands, and in turn it is not covering the surface properly. So, in turn it will lead to poor lubrication, and it will enhance the surface stresses, and it will eventually lead to enhancement of the frictional forces also. So, we will observe a very high coefficient of friction. So, again the lubricant what we are choosing, it has to be wetting enough for the surface, so that it can spread out and it can protect the surface from the wear damage. Also, we can have self assembled monolayers on the surface. So, they also act as molecular spring. So, once we have a surface, we can have some protection because of the monolayers. They can be Langmuir-Bloggett films as well, or even silines, or there can be many types of self assembled monolayers. So, they can stay on the surface, and any tip when it interacts with the surface, these act as springs, molecular springs. So, the overall loading which is being incurred by the tip does not reach the sample directly, but it is via through a Langmuir-Bloggett or Bloggett or self assembled monolayers. So, what we can see, the damage to the sample now is restricted. So, if the molecular springs, they have very high compliance, it can take very high loads or very high shocks. So, in turn we will see a very low friction and wear in those cases. So, we can see we can have a chemically bonded surface, but then it also is dictated by the superhydrophobicity or hydrophobicity, the viscosity of the film, or even the surface properties. Those are being changed by the chemically bonded lubricant films. Also, the self assembled monolayers such as Langmuir-Bloggett. So, they can, what they can do, they can act as a cushion, they can act as molecular springs. So, the kind of loading which is being supplied by the probe or the frictional tip, that is being absorbed by the molecular chains or molecular springs, and when the compliance of those springs or those molecules is pretty high, it can reduce the coefficient of friction and reduce the wear damage. So, nano scratching can be observed as a tip which is basically being interacting with the matter. So, depending on whether the matter is pretty like a particulate, so it can basically penetrate through, and depending if the surface is pretty hard, this is a tip, this can be particulate, it can be even hard surface. So, depending on how the response of this particulate or the hard surface is, it can either leave a scratch. So, it can leave a scratch in the material. So, just seeing the top view, or it can get embedded much deeper into the particulate and eventually can lead to very high coefficient of friction. Because in this case what is happening, the tip can pierce through the material, and in turn it will become very hard for the tip to walk across. So, once we have very high, it is more like a sand, and we are putting a needle inside and we are trying to move the needle. So, if you take a tip, try to insert it into the sandbox and trying to move it, it will be very harder for the tip to move. Whereas, if you take a surface, let us take a glass surface and take the same tip, same needle, and try to force it over the glass surface and move it along. So, we might realize that the hard surfaces might result a lower coefficient of friction in comparison to that of a of a sand surface. So, those can also come into picture. Additionally, what can happen, we can also add some lubrication, like generally people utilize graphite, or now these days people also utilize carbon nanotubes, and because of the graphitic nature they also can induce some they can also act as lubrication, and they can also absorb shock. So, as we saw in the self-assembled monolayers, that if we have a compliant spring, it can also absorb the shock, plus the graphitic nature of this carbon nanotubes, it can also tend to reduce the coefficient of friction, can be dramatically reduced. So, we can see that the overall feel of adding this aspect of nano scratching, it depends on the surface directly, that whether it is a particulate or a hard surface, and how are they interacting with the surface. So, it is more like a sand and a needle kind of a relationship. In this case, it can be a flat surface plus a needle. So, we can see that the lower coefficient of friction can be obtained when we have flatter surface. So, higher perturbations will cause very high coefficient of friction, and these days people have started adding some carbon nanotube also as a lubricant, because it can also act as an absorber for the shock, similar to that of self assembled monolayers. Also, it is very compliant. Also, because it has a graphitic nature, it can also reduce coefficient of friction. So, if we utilize this nano scratching or micro scratching, and if you are utilizing say a Berkovich tip, we need to utilize the equivalent of this conical angle. So, the conical angle equivalence of this Berkovich tip is around 70.3, that has been utilized here. So, we can see if the tip is scratching the surface, we can utilize the rule that it is forming a conical entity or a semi triangular entity throughout the length. So, defining its depth and the length, we can always calculate what is the wear volume. So, depending on the geometry of this particular cavity which has been created by a movement of this particular tip on a surface, we can always calculate what is the wear volume that is being arising from the nano scratching or even at a micro scratching. So, that is the wear length, this is the depth, and then we have a equivalence of this particular conical angle for the Berkovich tip. So, from that we can always calculate what is the wear volume. But more essential is to be able to correlate what is happening at nanoscale and at micron scale. So, we can see that the overall wear constant is dependent on the wear volume, hardness of the material, and the kind of loading that has been applied. So, we can obtain the wear constant and equating that. So, because we can also find what is the fracture toughness. So, for a brittle material, we need to see what is the crack length or what is the fracture toughness exponent. So, we can see that it has a dependence on the Ka. So, K this is the exponent for the fracture toughness, this is the K is the fracture toughness. So, we can see that this K power A equal to H power B. So, wear volume is equal to 1 by Ka hardness over B. So, we can see that the wear volume is inversely proportional to the when we have very high fracture toughness or when we have very high hardness, we can see a wear volume can be very low. So these exponents also are very critical, A and B, because now if they are very high, the overall contribution from fracture toughness will also be very high. So we want this fracture toughness exponent to also be very high. So depending on which type of material is there, we want A and B to be very high. B is approximately 1.5 for ceramics. So we can see that the contribution of A is also very strong. So once we can identify what is the value of A and B, then and from the wear constant we can also input this wear constant into K. So what we can see, the coefficient of friction which is arising because of the nano scratching, the kind of crack line that is being generated, we can always calculate the critical pressure which can cause cracking. So eventually what is happening, we are utilizing to identify the fracture toughness, hardness, and from nanoscale we can always find what is the frictional coefficient to cause cracking in the material. So through this particular relationship we can identify wear constant, we can get A and B exponents, coefficient of friction from the nanoscale experiments, and eventually we can calculate what is the contact critical pressure to cause cracking. So by utilizing the this particular technique of nano friction or nanotribology, we can always go back and identify what is the kind of force or pressure required for causing this particular cracking. So essentially what is happening is we have to correlate what is happening at nanoscale, microscale and the macro scale. So kind of testing that is required. So at subgrain we are talking about nano indentation or nano scratching, at micro scale we are talking about fretting, and at macro scale we are talking about pin on disc. So how we can correlate these aspects in terms of what is the fundamental mechanism, in terms of their microstructure, in terms of the component geometry or the bulk features. So how we can correlate? So we can obtain properties or the fundamental mechanism at nano level, be able to correlate it to the microstructure and eventually form the design part via seeing the bulk features or the component properties. So this becomes very essential in correlating the hierarchical structure which is dominant at 3 different length scales. So in summary, we can see that the contact and friction at nanoscale is very different because of the tip contact area, kind of van der Waals forces, kind of contact forces which are dominant at that length scale. It depends more on the slope rather than the peak height or the peak depth. Also we saw the dependence of the tip radius. So as soon as we are talking about higher and higher tip radius, we are enhancing the contact area. So we are eventually inducing very high frictional forces which are to be required. So we can see increase in the frictional forces. Also length scales also become very critical because of the kind of loading conditions, the dominance of certain mechanisms like flowing is very limited in the nano length scale. Even the hardness of surfaces are very higher in comparison to that of bulk. So length scales also contribute a lot in terms of dictating the frictional properties. Role of environment, like once we have humidity, it will also lead to enhancement in the overall meniscus bridges to a certain extent, but then it will start acting as a lubricant. So then in turn it will start reducing the coefficient of friction. And also how we can utilize all these concepts in going from nano to micro. So at nano we can find the mechanism, and micro we can also include the overall contribution from the microstructure, and then we can come to the design of the component. So in that case we can see the overall relation of nanotribology in eventually coming out with the mechanism and finally designing a real life engineered component. With this I end my lecture. Thank you.